Okay, the third topic is about the rotational motion control of cholesteric liquid crystal droplet. And cholesteric liquid crystal is in each layer, molecules align in one direction, but each layer gradually change the orientation angle. That's one of the hot topics in the liquid crystal field. And it was discovered that the cholesteric liquid crystal rotate. It was about more than 100 years ago by Professor Lehman, which is called the Lehman effect. However, this experiment was not so repeatable, and quite recently, Professor Oswald found a good experimental condition to have a stable condition of the Lehman rotation, which is the liquid crystal must be in a liquid crystal of the isotropic condition. So liquid crystal droplet inside the liquid crystal. Under this condition, Professor Tabe studied this system very well, and she found photo-induced rotation in this very kind of special condition, cholesteric and liquid crystal isotropic condition. However, recently, Professor Araoka found that this rotation could be possible in an aqueous solution too. So what we are trying to do is we want to control this rotational motion in aqueous surfactant solution by light. So what we did is here, as a photoresponsive liquid crystal, we again use MBVA. And we added chiral dopant S811 and R811. As an outer fluid, we use a PVS solution because SDS was too strong to solubilize. And in this case, we use the inverted microscope again for observation, but the UV LED was illuminated from the top side. Then here's a demonstration of the UV on-off operation. So when the light is on, start rotating, and you could see this a spiral pattern changing. And also by changing the chirality of dopant, actually the motion direction was opposite. And then when the light is off and probably on again, like this. So surely we could demonstrate the rotational motion by light. So light-induced control of rotation was possible, and by changing the chirality of dopants, the rotational direction could be controlled. And then here's the UV light intensity dependence. There's some threshold intensity because probably it's sticking to the substrate. And then once it starts rotating, it's almost linearly increasing the rotational velocity. So obviously the light induced, this must be the light induced rotation. And here's the mechanism of this rotation. So just briefly, I'll explain that this one was theoretically explained by Leslie, and this is a torque of the droplet. And what you need is, in this case, at this time, only the thermal gradient could induce the motion. So here's a thermal gradient direction is parallel to the parallel or anti-parallel to the torque. Here's torque, and the N is indicate the molecular orientation. So, so what we need is, here's a temperature gradient, but in our experiment, we illuminate the UV light. So if the UV light irradiation gives us some inhomogeneous distribution, it could generate some sort of the gradient force, such as chemical concentration gradient or thermal gradient. So we studied the light penetration experiment, and we found that the light was mostly absorbed about 20 micron, and compared with the size of the droplet, about 100 micron, which is quite smaller. So there should be some sort of the gradient force. So here's a motion mechanism we are thinking about now, and still there's some unknown parts, but initial condition of the liquid crystal shows a double spiral pattern, which can be explained by the molecules gradually in the radial direction. It's gradually rotating, and that makes this kind of pattern. And once the light was illuminated, this pitch was expanded. This is, and also the Lehman torque was induced. We still don't know this pitch expansion or the torque itself gives the origin of the torque, but definitely there will be some chemical concentration gradient or thermal gradient. So some gradient forces applied, and which induced the expansion of the pitch, and at the same time the stuff rotating due to the torque induced in for the droplets. And this one was recently published, so please check it if you're interested. So with this, let me summarize my talk. We demonstrated the photoresponsive liquid crystal or diode of liquid crystal by light, and the motion was induced by the convective flow due to the control of the molecules absorbed or dissolved from the surface or interfaces, and then the motion direction could be controlled by just minor change of the light absorbing molecule. And also we could control the rotational motion of the CLC droplets, and the motion direction again can be controlled by the chirality of the dopants. And with that, thank you for your kind attention.